Good afternoon. So what we are going to today about problem is about that h of z equivalents to 1 by z inverse z minus 0.5 z inverse into z inverse of z minus zero point 0.5. Okay. So we'll be considering of one b equivalents to 3 bits. Okay. So let me do over here. So when you are doing multiplication, the denominator z power minus 1 will lead to z power minus squared. So when it goes into numerator, we'll get the value around z square divided by z minus zero point 0.5 into z minus 0.45. The roots of the denominator, which to be the original poles of the equation. So the poles are to be the zero point 0.5 and 0.45. Okay. So let the original poles, which should be given as an over here. Okay. Now let me use of a direct form. So when you are using a direct form, so that can be replaced by means of an 1 by 1 minus zero point 0.5 z inverse of 1 by 1 minus zero point 0.5 z inverse. So when you are multiplying these two values, so we can able to get that 1 minus zero point 0.5 z inverse minus zero point 0.4 z power minus 1 plus 0.22 z power minus 2. So let me convert all these coefficients by means of one truncation. So when you are replacing the value of 1.95, that has to be converted into binary value. That will be converted into binary value. So we'll be getting the value around 0.412. So when it is truncated to 3 bits, so it will be given the value to be around 0.111. So again, when you are converting it into decimal, we can able to get a value around 0.875. Okay. So after that, again, when you are doing the conversion for 0.225, it is truncated to the value. We can able to get the value around 0.0011. So when it is converted into one decimal value, it will be getting around the value to be 0.001. And then when you are converting into decimal, we will be able to get the value around 0.125. So let h of z be the transfer function of the I after counting the coefficients. So it will be equivalent to 1 minus 0.875 z power minus 1 plus 0.12 z power minus 2. We know that h of z equivalent to y of z divided by x of z. So this will be equivalent to y of z divided by x of z. So 1 by 1 minus value. So do the cross multiplication. We can able to get the value y of z minus 0.875 z inverse y of z plus 0.125 z power minus 2. Y of z is equivalent to x of z. So again, y of z is equivalent to x of z plus 0.875 z inverse of y of z minus 0.125 z power minus 2 of y of z. This is the way to do their cascade direct form one. Similarly, when you are doing in the case the form of one cascade form, we can able to get that h of z is equivalent to 1 by 1 minus 0.5 z inverse of 1 minus 0.45 z inverse. In cascade realization, system can be realized as an cascade of first order section. So we'll be dividing off into two sections, H1 and H2. So H1 of z is equivalent to 1 by 1 minus 0.5 z inverse. When you are truncating the value of 0.5, it will be equivalent to 0.1000. So we have to truncate into 3 bits, so it will be equivalent to 0.100. When you are converting into decimal, we can able to get the value around 0.5. Similarly, when you are converting 0.45, the binary value equivalent will be equivalent to 0.111. When you are converting into 3 bits, it will be equivalent to 0.011. So finally, when you're converting into decimal, we can able to get the value of 0.375. The H1 of z and H2 of z be the transfer function of first order section after contacting the coefficients which are to be given as over here. So H1 of z is equivalent to 1 minus 0.5 z inverse. H2 of z is equivalent to 1 by 0.375 z inverse. So H1 of z is equivalent to y1 of z divided by x1 of z. So 1 by 1 minus value. So do the cross multiplication. We can able to obtain the value of y1 of z. Similarly, H2 of z, y2 of z divided by x2 of z is equivalent to 1 by 1 minus 0.375 z power minus 1. So after doing the cross multiplication, we can able to get the value around y1 and y2. This is the way we have to do over the cascade multiplication direct form realization. The next one, we have to be detailed about round off effect in digital filter. The presence of one or more quantizer in the realization of a digital filter results in a nonlinear device. That is, a recursive digital filter may exhibit undesirable oscillations in its output. In the finite arithmetic operations, some registers may overflow if the input signal level becomes large. These overflow represents nonlinear distortions leading to limit cycle oscillations. There are two types of limit cycle oscillations, which includes one to be the zero input limit cycle oscillation, another one to be the overflow limit cycle oscillation. So when you are making a zero input limit cycle oscillation, the arithmetic operation produces oscillations even when the input is zero, or some non-zero constant values. Such oscillations are called zero input limit cycle oscillations. Overflow limit cycle oscillations. The limit cycle occurs due to the overflow of adder is known as overflow limit cycle oscillation. When you are defining the deadband of the filter, the limit cycle occurs as a result of quantization affecting multiplication. The amplitude of the output during a limit cycle is confined to a range of values called the deadband of the filter. So when you are taking the modulus of the value of n minus n, which is to be less than or equivalent to 2 to the power of minus b divided by 2 divided by 1 minus modulus of alpha. Consider the first order filter y of n is equivalent to a of y of n minus n plus x of n, where n should be greater than or equal to 0. After rounding the product, y of n is equivalent to quantized value of a of y of n minus n plus x of n. The round of error value will be equivalent to minus 2 to the power of minus b by 2 less than or equivalent to e power r less than or equivalent to 2 to the power of minus b by 2. So which is nothing but a difference between the quantized value and the actual value. So q of a of 1 minus n minus a of 1 minus n should be less than or equivalent to 2 to the power of minus b by 2. The deadband of the filter for a limit cycle oscillation is that q of a of n minus n is equal to, when a is greater than 0, the value will be equivalent to y of n minus n. Similarly, when a is less than 0, minus a of y of n minus 1. So finally, we can able to take the modulus of this value. So y of n minus 1 minus a of y of n minus 1 should be less than or equal to the power of minus b by 2. So y of n minus 1 into of 1 minus modulus alpha should be less than or equal to 2 to the power of minus b by 2. The red band is equivalent to modulus of y of n minus 1 should be less than or equivalent to 2 to the power of minus b by 2 by 1 minus modulus alpha. Let me consider the, let me calculate the problem by using a deadband filter. Let me consider the first order FAR filter equation. Y of n is equal to x of n plus a of y of n minus 1, with x of n is equal to 0.875 for n is equal to 0, 0 otherwise. Find the limit cycle effect on the red band. Assume b is equivalent to 4 and a is equivalent to 0.95. Given that x of n is equivalent to 0.875 for n is equal to 0, 0 otherwise. Deadband 2 to the power of minus b by 2 of 1 minus modulus alpha. So 1 minus 0.95, so which is equivalent to 0.625. So y of n is equivalent to x of n plus 0.95, y of n minus n. So we have to substitute for n is equal to 0, 1, 2, 3, 4, 5. So this has to be repeated over on it. So if you are taking n is equal to 0, the value of x of n is equivalent to 0.875, y of n minus 1 will be 0, a of y of n minus 1 will be 0. So round up to 4 digit will be equivalent to 0, and then finally the y of 0 is equal to 0.875. Similarly, for 1, the x of n to be 0, we have to consider the previous value 8.75. Then we have to multiply 8.75 into 0.95. So we have to take the binary values and the decimal values, then round off into digits, then finally y of n. Similarly, for 2, 3, and then 4, we get the value around y of 4 is equivalent to 0.625. So when you are doing over for the 5 and 6 continuously, what we can able to get over on the winner, we can able to get the value of around y of 4, y of 5 and y of 6 to be 0.625. The red band of the filter is 0.625. So for when n is greater than or equal to 5, what we can able to observe is the output remains constant at 0.625, causing the limit cycle oscillation. Okay. So this is the way to compute your dead band cycle. So the remaining we can see in next class.